Thanks for the introduction. I'm Yinkang from Xi'an Jiaotong University. Today, I'm going to talk about SMT-based fault-tolerant verification for wide area networks. Network outages are actually very common. According to Cisco standards, there are more than 1,000 network outages on a single day. These outages can cause significant economic losses. The primary reason behind these outages is human error. In fact, report of Uptime Institute shows about 64% of network outages are caused by human errors during network configuration changes. So why are wide area networks so airborne? The first reason is their irregular topology structure. As we can see from this real-world topology, just carry from topology rule. There are no central nodes, there are no clear hierarchical layers. This is mainly because wide area networks are often deployed at a global scale, and their physical connectivity is constrained by geography factors. The second reason is that each device is often configured with complex routing policies. In practice, operators often use advanced configuration features, such as route reflectors, route aggregation, and BGP communities. These features make manual misconfigurations much more likely. To avoid such misconfigurations, operators want to know whether network properties still hold after link failures. We take the reachability from Greensboro to Atlanta as an example. A fault tolerance value of 1 means that Atlanta can still reach Greensboro even if any one link fails. Moreover, operators may also want to verify other properties, such as web pointing, which asks whether packets will always traverse a specific node, and load balancing, which asks whether traffic can still be forwarded along multiple distinct paths. However, the fault tolerance value is not easy to determine. When only considering topology connectivity, packets sent from Greensboro to Burlington have two distinct paths, so the tolerance value is 1. But some paths may actually be blocked by routing policies. For example, the device in Burlington is configured with a routing policy. The policy permits a larger range of prefixes with low priority, while denying a smaller range of prefixes with high priority. Finally, it drops all routes whose prefixes start with 192. As a result, packets will be blocked at Burlington, and the final tolerance value becomes 0. Therefore, the tolerance value cannot be determined solely by the network topology. We must also model the network configurations, otherwise the computed tolerance value may be incorrect. To address this problem, SMT-based verifier have been proposed to help operators. The earliest method, Minesweeper, introduces an SMT-based encoding framework that is still widely used today. Specifically, it encodes the verification problem into a set of SMT constraints. Here, A represents the network, P represents the property, and K represents the fault tolerance requirement. If the constraints are unsatisfiable, it means the property holds. Otherwise, if the constraints are satisfiable, the property is violated, and the SMT solution provides a current example. We next introduce how the network is encoded. Minesweeper proposes a model where each node has import and export filters, and the routing policies are modeled as either import filters or export filters. So when routes are propagated, these filters perform their corresponding actions, such as modifying or dropping routes. Let's look at the previous routing policies as an example. Minesweeper will encode routing policies as SMT constraints. Specifically, it uses a single SMT variable, a 1-bit flag called valid, to represent whether a route remains valid after passing through a filter. The prefix and the prefix length variables are used to model IP prefixes. Based on these variables, Minesweeper can model prefix matching between routing policies and routing messages. For example, this SMT constraint fragment of FBM means that if a route matches the filter, the valid flag of the route record becomes false. In other words, the route will be dropped. After devices collect routes from their neighboring devices, Minesweeper uses SMT constraints to model the vector selection process. For example, the best route on V7 can be represented by the following constraints. The first part of the conjunction represents the selected best route has the minimum preference cost. The second part of the conjunction ensures that the best route must be selected from one of the neighboring routes. We next introduce how encoded property. For the property can router V1 reach subnet D on route V2. MySweeper define a variable can reach V, which indicates whether node V can reach destination. For example, for V2, can reach V2 directly represents whether V2 can reach destination. For can reach V1, the definition becomes recursive. If holds if either V1 falls to V2 and V4 can reach destination, or V1 falls to V3 and V3 can reach destination. Finally, the original problem can router V1 reach subnet D on route V2 is transformed into an SMT satisfiability problem, and we only need to check whether can reach V1 is satisfiable or not. For encoding tolerance value, MySweeper encodes the encoded tolerance value as the number of failed links is less than k. But unfortunately, the encoding method of tolerance value leads to a scalability problem for SMT-based verifiers. For example, in a user carrier topology with 192 links, by selecting 3 failed links, the SMT solver may need to deploy up to 1 million link failure combinations. As a result, verifying a single property can take around half an hour, and verifying 300 intents may take up to a week. So, can we verify a single property at a minute level? One type of speed-up method focuses on optimizing the solving process. For example, by reducing encoded variables, adding extra constraints of the solving process. Another type of method is speed-up verification by simplifying the network model. For example, they modelize the network or abstract wide protocol details. However, all these existing methods have their own limitations. Bonsai and origami only work for symmetric network topologies. Biode and Trailblazer rely on stronger assumptions, such as the direct fault policy model. NetSMT only handles cases where the property is violated. When the property actually holds, it still needs to explore the full search space. Other tools such as timepiece carigami Logier lose their ability to verify for tolerance properties. Let's take Trailblazer as an example. It reduces the SMT search space by focusing only on links along floating path. For instance, consider reachability from V1 to V7. Under this network, the floating path is marked by balloon lines 1, 2, 4, 2, 5, 2, 7. Due to the routing policy, the routing path is different from the floating path and marked by green lines. Trailblazer takes a strategy. Instead of exploring all possible failure combinations, it only considers failures on these 3 links, resulting in only 3 failure scenarios. Finally, Trailblazer thinks for reachability from V1 to V7, the tolerance value is 1 link, but ignore routing path. It may also influence the behavior of properties. For example, when the link V5 to V6 fail, there is no available route from V1 to V7, so V1 cannot reach V7. In this case, reachability from V1 to V7 is already violated, even with only 1 link failure, and the tolerance value is 0. Therefore, Trailblazer may produce false positives. Therefore, we propose VeriBoost, which does not assume a regular topology structure or any specific routing policy. Recall that the basic constraint is the conjunction of N, the negation of P, and K. We denote the set of all links from topology as L, and the failed links are selected from the space L. Now, suppose we can design the set of some links as down or up before verification. Then, we can restrict the failed links to the remaining link space S, instead of the whole space. With this way, SMT solver doesn't need to explore up all combination of failed links. Next, we introduce how to find the down links. We take the reachability from V1 to D on V2 as an example. We consider the routing path at first. Note that routing and forwarding directions are opposite. First, D is connected to V2, so in the routing table of V2, the D is connected and the S path only has only V2. Then the bachelor route of V2 is spread from V2 to V7. Because the route is spread from V2, so in the routing table, the next hop to destination is V2, and the S path has extra node V7. Next, the bachelor route of V7 is spread from V7 to V5. Next, the bachelor route of V5 is spread from V5 to V4. Here, V4 may announce routes to V10, then routes will spread along V4, V10, V9, and then arrive at V4 again. So the routing table of V4 currently has two routes. However, because the path of the first route is the sub path of the second route, the first route have the more short S path length. So the second route isn't the best route and will be deleted from routing table. Finally, the route from V2 to V1 is spread along the path V2, V7, V5, V4, and V1. We noted that these three links don't spread the bachelor routes. Even routes spread from another path, these three links still don't spread the bachelor routes. The essential reason is that route will prefer to spread by loop-free path. Therefore, this link is irrelevant and can be set as done status before verification. Here we define simple path as a path have no repeated nodes, and we summarize a theorem. If a link does not appear on any simple path, then the link is irrelevant and can be set as done. For the rigorous definition, see our paper. Now we introduce the idea about finding up links. Suppose the bachelor routes spread via this path marked by blue lines. When we found link V5, V6, route cannot spread by node V6. The bachelor forwarding route change into a new path. When we found another link V6, V8, we find that the routing path changes into the same new path. So we find failing these two links have the same influence to the forwarding behavior. We don't need to fail them separately. We summarize, some links is equivalent and one of them can be set as up before verification, so also for the rigorous definition, see our paper. To this end, with this simple idea, before reducing the link space, the link space has 12 links, and the failure scenarios are 220. After reducing the link space, the failure scenarios become 10, reducing about 20 times. But unfortunately, enumerating all simple paths is an NP-hard problem. It takes much longer time compared with verification. Moreover, checking equivalent links is a chicken and egg problem, as we want to speed up verification, but it requires verification again. We therefore propose link pruning and link compression methods. Link pruning is targeted at finding all simple paths without enumerating all paths. We introduce PPC at first. PPC is a subgraph that removing any single link still preserves connectivity between every pair of nodes. For example, in this toy network, PPC31 has 4 nodes, V1, V3, V4, and V5, and this network has 4 components and 3 card points. Then, link pruning maps card points and components into new nodes, and it uses card points and components to build a new graph. This graph is proved as a tree structure. Then, link pruning traverses the tree to identify all feasible paths. This step is used to find bi-connected components that must be passed from the source node to the destination node. After it combines all links in the traversed components as the relevant links, and the complete set is the irrelevant links. In this example, 3 links V9, V10, V4, V9, and V4, V10 are irrelevant links. Recall that again, with this method, we find all links in simple paths without enumerating simple paths. We also provide the theorem to confirm the correctness of link pruning method. See our paper for details. For finding uplinks, we adopt a strategy. Instead of identifying all equivalent links, we try to find a subset of equivalent links. We first define trivial path. If all nodes within the path except endpoints, their degree is 2. This path is trivial path. For example, we show two trivial paths in this network topology. We find that if the degree of node 2, then the adjacent links are equivalent. For example, V5, V6, V6, V8 are equivalent, and V6, V8, V7, V8 are also equivalent. The reason is failing both of them blocks the route from choosing this subpath. Moreover, the equivalence of this link is transitive. Therefore, V5, V6, V7, V8 are equivalent. We also provide theorem to prove the correctness of this method. We summarize the links in trivial path as equivalent. See our paper for more details. We also take a common user optimization called property trimming. If tolerance value of a property to be verified is key, there must be more than key disjoint path in the property. If the property doesn't satisfy this requirement, we could directly return property is validated and don't need to verify. We next introduce the implementation of VeriBoost. It takes their topology configurations in a single property as input. After pruning the link space through link pruning and link compression, the remaining space is input to SMT-based verifiers. Then it outputs whether the property holds or is validated. For verifying multiple properties, we could repeat the above steps. We implement VeriBoost in about 4,000 lines of Java code, and we have also open sourced it in our group website. For evaluation setup, we use 260 real WAN topologies from Topology Zoo and 9 configurations from NetSMT and config2spec. These configurations are across small, medium, and larger sizes. Here, we use O to represent OSPF configurations and the either I BGP configurations. We check 3 types of properties, including reachability, web pointing, and load balancing, with their tolerance value set as 0, 1, 2, and 3, respectively, and we select 25 pairs. Therefore, for each network, we will verify 300 properties. We first conduct a case study to intuitively illustrate the effectiveness. For the real-world topology of the US carrier, we explore can Greensboro still reach Atlanta if any 3-link fail. We can see that VeriBoost could find lots of irrelevant links marked in red circle and equivalent links marked by red lines. Before applying VeriBoost, the combination of failed links is 1 million. After applying VeriBoost, the combination of failed links is 10,000. It reduces the failure scenarios by 2 orders of magnitude. This example shows that VeriBoost can indeed reduce a larger number of failed scenarios. Finally, it finds that property is validated when these 2 links fail. We also evaluate VeriBoost across 260 real WAN topology. The results show that for worst case, VeriBoost can reduce 50% of links for 60% of topologies. For average case, VeriBoost can reduce 78% of links for 80% of topologies. These evaluation results show that VeriBoost is effective across different types of network topologies. Moreover, we also verify the correctness of VeriBoost. The evaluation results show the property verified by Minesweeper, SMT, and VeriBoost are identical. This proves that VeriBoost is correct. Besides, to evaluate the speed up, we conduct experiments on 9 networks and vary the fault tolerance parameter. VeriBoost accelerates Minesweeper by 2 to 47 times, while the state-of-the-art method achieves only a 2 to 3 times speed up. This shows that when the tolerance value is larger and the network is more complex, VeriBoost achieves greater speed up. and all pre-processing steps, including property trimming, link pruning, and link compression, take only milliseconds to complete. Compared with the verification time at the minute level, this pre-processing overhead is negligible. In this talk, we show that verifying fault tolerance for WANs is challenging due to the huge failure scenario space, and the existing speed-up methods are limited to symmetric topology structure or specific routing policies. We propose VeriBoost to improve scalability, and it achieves 2 to 47 times speed-up with millisecond level pre-processing. Thanks again. For more details, please refer to our paper. I'm happy to take any questions.